So we're going to go through the different stages of like the electronics design process. We're going to do it in Fusion, and we're going to walk through making like an actual useful circuit and turning it into a PCB. So by the end of this little workshop, you guys will know how to import parts from DigiKey to Fusion, make a Fusion schematic, and develop that schematic into a Fusion PCB layout that you can then download and manufacture as you want. All right, welcome to ECAD. So I'm not going to be going super in depth on like the actual like EE stuff. Like I'm not going to expect you guys to know how to do the math for, I'm not going to walk you through the math for like capacitors or anything like that. I kind of assume that you're going to have a reasonably working knowledge if you're going to actually be doing this. Otherwise, you'll have to do some research and learn about that. But this is the layout we're going to be making. We're going to be making a missing pulse detector using a 555 timer. And in the end, you'll be able to make this, hook it up to an Arduino or something, and detect missing pulses in a signal. So if you were a EE and you were like doing this for your job, there's the kind of a design process you would follow, similar to the like product design process at any other stage of engineering. So it starts with specifications. So you're usually going to be handed a list of things that your design needs to do and the performance it needs to achieve for those different requirements. So it'll be like your operating voltage, what temperatures you're expected to be at, how big your PCB can be, and then of course like the things it needs to do, the parts you need to use, stuff like that. It's just a list of things you start with, and then it's your job to move into the next step and turn that into a schematic. So typically when making a schematic, you do want it to be as detailed and accurate as you can get. This is like the most intensive part of the process usually, because it requires a lot of iteration, a lot of design review with like your mentors and things like that to make sure it's a really useful design. There is a little bit of difference in PCB schematics versus like a fritzing schematic. In the PCB schematic, you have to always be thinking about, I am turning this into a physical thing. So every single part you place on the schematic represents directly a physical part on your PCB. And that's really important to keep in mind when it comes to things like part numbers, sizes, where you're going to be ordering them, stuff like that, because you have to include all that information in the schematic. Otherwise, you're going to move to the layout and have no idea what's going on. But once you're done the schematic and it's passed through the review phase, you move into the layout, which is really just moving the parts onto the board, making sure you meet all the like ESD and temperature requirements and follow all of that. There's like a textbook of like PCB requirements that most like professional EEs have to use for different classifications of product. So for example, there's like class 1, class 2, and class 3. And for PCB design and soldering, class 3 is like military grade, and class 1, I think, is like sketchy Amazon product. Most companies operate in class 2 to class 3, but you don't need to care about that at this stage. But that's where a lot of those design factors would come into play. Again, there's a design review process. And then once it's approved, you move into prototype and production. So we're just going to be doing specifications, schematics, and layout today. We're not going to go heavy on the like procedural stuff. This is more just an introduction, but the design process is good to know if you ever are interested in doing this in industry. EE jobs in industry are a lot of this, schematics and layouts. All right, so we're going to go to Fusion and we are going to get set up to make our schematic, and then we'll get diving into it. So when you first open Fusion, if you've ever used Fusion before, you're familiar with this screen. This is just like the blank screen. You've got all your manufacturing things, but we don't want any of that. We want over here to go to new electronics design. So it'll add this little page to whatever folder you're working in. And we are going to get rid of the Mechie stuff. What's up?
I believe you're only screen sharing your Google tab, not your Fusion.
Oh, weird. I thought it was just like a window because I just opened it in my window. Okay, interesting. Um, thanks for letting me know. Let's try that again. Can you see it now?
Yep.
Okay. Good. So it just opened on the normal screen. I went to File and New Electronics Design, and it brings you to this page. In your whatever folder you're in, it just adds a New Electronics Design. So this page right here links together your schematics and your PCB. You always have to open this first before you can edit a schematic or PCB because it has to maintain the references. So like, for example, this is the demo I did for making this workshop. This is the main electronics design. This is the PCB and this is the schematic. And you have to open this before you can effectively edit these guys. But we're making a new one. So this is the link page. And you can make any number of schematics and PCBs in here, and they'll be linked together, I believe. So we're going to make a new schematic. That'll come in here. I'm just going to save it real quick. And then notice how that updates it over here as well. And we now have a schematic in our main organizational page. So the important things to know in the schematic UI, if you've never used this before, over here on the side, you have kind of the different tabs that you'll be using. The one you use most often is Place Components. This is all the components Fusion sees either in your computer or already in Fusion. And from here, you can drag and drop and add different parts to your design. So we're going to be using this one a lot. They're organized into libraries. It's kind of similar to using like pulling functions out of libraries in code. If you're more software focused, you can think of these as a package, and each of them has a handful of parts in it that we're going to just use in our main workspace. So Place Components is pretty useful. Up here we have our wire routing and naming stuff. So this is make a wire. You can name, add labels, do ports, all kinds of fun stuff. Fusion does have a simulation tool. I haven't used it too much. I usually just do Spice, but you can add Spice models to this, and you can add probes and sources and kind of run a quick demo, assuming the parts you're adding have simulation capabilities. The other ones up here that I use a lot are the like movement pieces. So move, rotate, and mirror to just kind of move your parts around and organize them. And then adding values can be real nice as well. So it's not too crazy. You don't really have to care about this much, and you just make your schematic here. So what schematic are we going to be making? I'm going to manually reshare my screen so that it works. We're back in the PowerPoint, right? You guys can see this? Yeah? Okay. Stop doing that. Okay. So like I said, we're going to be making the missing pulse detector. So this is something you might need to make in industry. I don't know, but it's a pretty useful circuit if you're analyzing signals. Like let's say you have a specific like PWM or something signal or a sensor signal that you're reading and you're getting weird errors and you don't know why. Well, maybe you're losing pulses somewhere, and that means there's something wrong with either your layout or the sensor you're using. And so you might want to design a quick little circuit to test that. So this uses a 555 timer, which are used all the time in like hobby electronics and things for controlling LEDs, for controlling computers and like processors. They're essentially a clock that you can control, turn on and off, give it different frequencies, all that cool stuff. So our specifications for the circuit is use the 555 timer, power it with the Arduino, and detect missing pulses from an input Arduino signal. And then we're going to output detect the information that we're getting from this circuit back into the Arduino for analysis. So this might be something you would get handed to by your boss and be like, I need you to make a missing pulse detector. Here's what it has to do. We're not going to worry about temperature requirements. We're not going to go too heavy on current requirements or power requirements, anything like that. This is just like an overview, and here's kind of the schematic for what we're going to be making. So the central piece of this is the, actually, is there any questions before I dive into this? I know I've been talking very fast. Okay. I think you guys will have to tap the mic if you want to speak, is what Jake figured out.
Oh yeah, no, it's a little mute button. No questions here.
Transcendent safety issue.
Okay. So the 555 timer is the most important part of this circuit. It kind of controls everything. So we need to go figure out how to actually make all this. So popping over here, this is the part we're using. I just searched it up on DigiKey and gave it the specifications I wanted. DigiKey is where I usually get all of my parts and components because it's just really easy to search and buy things. So this is a TI product. I usually look for TI products just because I think their data sheets are really useful. Active just means that they're still selling it, which is usually good. This is the frequency it can run at. So this is important if you're trying to interpret a signal that is running higher than this, you wouldn't be able to do it. So whatever signal you're trying to look at with the missing pulse detector, it would have to be at a frequency lower than 100 kilohertz. And you have to be operating between 4.5 and 16 volts, and you can't be using more than 10 milliamps. So these are all just like good things you need to pay attention to when you're looking at parts, keep in the back of your mind. The other thing that we specifically have to think about, since we're making a physical PCB, is what package this part is in. So the package is just like the shape of the part. Like, is it a through-hole part? Is it a surface mount part? How big is it? How many pins does it have? There's different versions usually for each, any type of component, and the different versions are used for different things. So for us, we're going to be using this package, the 8PDIP, which is parallel pins, basically. So it's just, there's 8 pins and they're arranged parallel to each other. This is pretty typical for through-hole PCBs, and they're really easy to solder. So that's what we're going to be using. Going now into the data sheet is where we can get all of the rest of the information we need. So data sheets are going to be your best friend when you are making any kind of circuit ever. Even sometimes I'll look at data sheets just for like capacitor parts I'm looking at, which like seems a little weird because like most capacitors behave the same, and you really only care about their rating. But every now and then you'll run into something and be like, wow, I really need the specifics for this part I'm using. And so data sheets are always there. They're going to be really important for you to get comfortable using. So they're, at least for TI, I really like their data sheets. They're always organized like this. General features for the product, a description of the product, just kind of giving you an overview of what it does, the different options you can get it in. So like I said, there's different packages you can get this guy, and a nice simplified schematic of how it works. Without getting into too much detail, the timer basically just has threshold and trigger as its main inputs, with power and then a couple of these other control signals that it uses. And it's taking these inputs, it's got a voltage divider, some comparators, and a latch circuit right here. The latch circuit is basically just what creates the timer. And then a little MOSFET down here. It's not super crazy. Table of contents, pretty standard. So these are the two main packages. Again, we're using this one. So this gives you your pin labels that we're going to use. And that's really nice to have. And it gives you a little description for each of those pins. Maximum ratings, I usually only look at supply voltage and current because like I don't usually end up caring about thermal stuff, but you might. We can't use above 18 volts, it'll break. We can't use more than 225 milliamps, it'll break. So these are kind of like your worst case scenarios that you have to design around. Your part should never experience these in your design. The recommended operating conditions is what your part can handle regularly. So it's what you expect it to be using generally and running at for the majority of its lifetime. So again, supply voltage, like it said on DigiKey, was 4.5 to 16 volts. Arduino is 5 volts, so that's perfect for us. Input voltage, again, it's the same as VCC. Output current can't get more than 200 milliamps. That's good to know because it means you can't really drive anything with the 555 timer. It's just for logic. So it's just going into a GPIO pin or something where you're not really drawing current from the device, you're just getting information. Thermal characteristics, more variables. We are going to end up only really caring about trigger. That's the only input we're going to be using for our circuit. And for 5 volts, we go right here to the NE555, which is what we've got. And we can see that it's these ones right here. So this isn't going to be a big deal for us. We can work around this. It just means that whatever signal you're trying to put on this input pin, don't have it go much higher than 2.2 volts. And not more than half a microamp. Thermal characteristics, fun charts that I usually ignore unless it's like something's broken. All right, this is the fun part. So this is where it explains how the device works. And this is usually after I go through like the min and max stuff, I go right to here because this is really what I care about when I'm designing a circuit to do a specific thing. So the functional block diagrams usually are more confusing than I need them to be, so I don't bother too much. The overview is nice. It just explains how the timer works. We're not going to get too much into that. We are going to be using monostable operation. So the 555 timer is cool because you can do it in 2 modes. You can do it in monostable and in astable operation. For the pulse detector circuit, it's monostable. So reading over this is usually a good idea. Basically, we're going to be using a capacitor and resistor network, and that's going to control the type of signal we can get. I'm going to explain all of this once I have the charts for the actual circuit because it'll be easier to explain them. So this is an example. This is some of the characteristics you can expect. For it just operating in a normal clock mode, this is that circuit. So this is whenever you get a low edge on your input, you get a pulse on your output clock. So if you can send it basically a clock pulse and get a different kind of clock pulse out of it, or you can just send it a signal in astable operation and get any kind of clock pulse out of it. Applications and implementation is what we are really going to care about because here is our missing pulse detector. So I just pulled this right from the datasheet. It gives you a nice example on how to do it and how, like what kind of values you'll need. So the important things here are RL, RA, and C. These are the resistor and capacitor network that kind of controls the circuit, and along with this transistor down at the bottom are what makes it a missing pulse detector. So can be used to detect missing pulses or long spacing between consecutive pulses. That's cool. It's re-triggered continuously by the input train as long as the pulse spacing is less than the timing interval. Okay, so that's good to know. We don't really know what that means yet, but it's probably going to be important. A longer pulse spacing, missing pulse, or terminated pulse then triggers the interval and generates an output pulse. Design requirements. The missing pulses must be high. So it cannot detect missing low pulses, and that'll make more sense in a minute. But if your input is stuck low, it's not going to be able to do it because this capacitor is not ever going to recharge. And so that's a really important design limitation that maybe means this circuit wouldn't work for your application. Or maybe you would have to have 2, one to detect missing low pulses and one to detect missing high pulses, using like an inverter or something. So this is really important. It's nice that they point this out for us. In our design instructions right here, we have to choose RA and C such that RA times C, again, if you're familiar with electronics, RC is the time constant for an RC circuit. So that's kind of makes sense there if you've taken like circuits 2 or something. And then this has to be greater than the maximum normal input high time. Okay, so what does that mean? That has to do with that thing we didn't know up here. So the pulse spacing has to be less than the timing interval. That's related to the maximum normal high time. So if we go down to this chart, the normal pulses on the input, that's the normal high time, right? And when it's longer, it detects it and you get a low signal until the pulse resumes. So this is what we're trying to make. And you can see what's happening with the capacitor here. It's charging and discharging normally, but once it gets to here, it's overcharged. So it's reached above this line and it's like, okay, I've been charging for too long. That means there's been a high pulse. We missed a low pulse, missing pulse detected. And then it'll drop the voltage, reset the capacitor and get back to normal. So this input high time for this example, and this example has RA as 1 kilo ohm and C as 0.1 microfarads, has a high pulse of less than 0.1 milliseconds. So again, RA times C has to be greater than just under 0.1 milliseconds, because you can see these don't actually go to 0.1 milliseconds. The high time is just less than that. So this design works perfectly. We're going to be using this schematic. So we're going to be using RA as 1 kilo ohm and C as 0.1 microfarads. And that means we can detect missing pulses for a pulse train with normal high, like a normal high period of 0.1, less than 0.1 microseconds. If, for example, the signal we were expecting had high pulses of 0.2 microseconds, we would just use a 2 kilo ohm resistor, and now that's good to go. So you can kind of see, like, it looks really confusing at first, but once you understand the requirements and all these charts, you're like, okay, I know what signal I'm working with, and now I can design the circuit accordingly. So like I said, the way it's doing that really depends on the capacitor, and the rate the capacitor is charging at is limited by RA. So that's why RA and the size of the capacitor control this, because this triggers whenever the capacitor is overcharged. So capacitor is overcharged, it triggers it. When the capacitor is charged normally, if trigger, which is your input signal here, this is trigger, input voltage. If this is high, that means your output is going low. So charged, it's high, you're going low. That's a missed pulse. When your output is already low, so you've detected a missed pulse, a negative edge on trigger, that's right here, resets everything and sets the output back to high. And what we need this transistor for now is that when trigger goes low normally, but your output is already high, you're not detecting a missing pulse because you're under the timer window. C is not overcharged. We actually want to discharge C so that it doesn't get overcharged. And the way they do that is by pulling that node here, this C, pulling it to ground using this PNP transistor. So PNP transistor, right, when the top node here, which is the source, is greater than the gate here and is also greater than the drain here, the transistor will turn on and sink current. So basically when your input is low and this is high, this is charged, this is low, it's a normal pulse because this isn't overcharged, you discharge the capacitor. Does that make sense? It's not important to what we're doing, but it's like good to know. Any questions on that? Okay, hearing nothing. It gives you a couple other examples of things you can do. You can actually make a PWM signal using a 555 timer, which is kind of cool. And it shows you what that would look like. We're not getting into that, but that's pretty sick. And then you can do a couple other things as well. Power supply recommendations. I don't know why they threw this all the way at the bottom, but we are going to need to take note of this. So designed to operate from an input voltage between 4.5 and 16 volts. Okay, we saw that. And then a bypass capacitor is highly recommended from VCC to ground. A ceramic 0.1 microfarad capacitor is sufficient. This you see all the time with ICs. Like linear regulators will do this. Any kind of like logic-based IC is probably going to want you to put a bypass capacitor between ground and VCC. And what that is for catching really high frequency fluctuations in your power supply. So it just happens sometimes on PCBs. There's many reasons that could cause it, but you don't want it to cause a change in the behavior of your circuit. So the capacitor just kind of catches that. It's a really small capacitor, so it's for high frequency signals. It'll just quickly discharge or recharge the capacitor and not affect your circuit. So it's just a little low pass filter basically that we're adding to VCC in front of the power to the device. Gives you some other links. This is why I like TI. They're just so nice. And then it gives you your packaging information. We don't care about that. So we pulled a lot of information out of this document, but it's everything that we need to design the circuit. What we're going to have to go do now is find a transistor that we can use. So this guy right here, and then build the rest of the circuit. So finding the transistor can sometimes be a little challenging. It's nice that it gives us one. However, I looked into it and this guy doesn't exist anymore. It's not sold on DigiKey, it's out of stock, it's not active. So we would have to find a new one. I already went through all that and did that for you. And it's just another PNP transistor that works at the logic levels we're using. It's not super exciting. But what we can do for both this and that transistor is I'm going to show you how to pull the part information into Fusion. So for this guy, we'll do this guy as an example, the NE55 timer. We got this page, we already looked at the data sheet. If we go down here to EDA models, this is what we care about. So it gives you all kinds of cool resources, but we need this. This is like basically importing the 3D model for a mechanical part. You have to import the electrical and schematic model for an electrical part into Fusion before you can do anything with it. I use Ultra Librarian mostly just because they have a really good selection. You do have to make like an account, but it's free. And this is what they're going to give us. So this is for our schematic, this is for our layout. And since Fusion lets you do 3D models, you can even get a 3D model of the part. So this is kind of what we care about. Notice how all the pins are mapped. It handles a lot of the circuits. Sometimes this will even include a SPICE model that goes along with it for that Fusion simulation. So we want to download. We want Autodesk. We want Fusion 360, and then you would download it. I'm not going to make you guys do that because we also need it for the PCB as well. So I'll just post this. This is just a link to a drive folder in our drive. And it has the library file, which is what you get out of this for both the 555 timer and the transistor we're going to use. So you download it, it drops you into a zip, it gives you a zip folder, you unzip it. Here's the 555 timer, Fusion 360 is what we got. Awesome. There's the 3D model, there's the Eagle library. Autodesk had Eagle before they implemented it in Fusion 360, so everything is still kind of in the Eagle standards. But this is our electronic information that we're going to need. So if you're following along on yours, I would just download those library files directly from the drive. But whenever you're looking for a part in your own designs, DigiKey, you can actually filter by whether or not it has EDA models, and then you just download it. Super nice, super easy. So I'm going to unshare back into Fusion. Any questions or anything? Cool. Back into Fusion. All right. Now we got to make the circuit. So we have those two parts. We have to import them into Fusion. They're not already in our parts manager. They're not one of the libraries we already have. Fusion comes with like a lot of things. Like it probably does come with the 555 timer already. It comes with some transistors. It comes with capacitors and resistors and all that. So you don't necessarily need to import every single part you're using. But for specific parts, I like to import them. So things like that specific model of timer, the transistor we're using, all that good stuff. And the way you import it is up here, open library manager. It brings up this page and it shows you all of the Eagle libraries you have on your computer. So all these ones at top are ones I've downloaded for my different things. And then these are all the ones it comes with. You can see all different brands, just so many different things. It's really nice. But we're going to import library from local disk. It pops us up into wherever you downloaded your Eagle stuff, and then you can just move into the location of those folders. So we want the timer. You just click that, click open, pops it in. We're going to do the same thing for that transistor, which is the NTA 4151 PTIG. Really exciting name. It's just a PNP transistor. All right, so those are in, and that means we can actually access those now from our place components. So we can go here and search for any 555. And let's see, we do get a couple. Which one's ours? This one is ours. So we are going to double click that. And as you can see, it automatically pops me up with the schematic symbol, and we can just left click to drop it anywhere in the schematic. It's nice. You can place multiple components, like if you have a resistor or something, you can drop that in. You can use your scroll wheel to zoom in and out. I use my press on the scroll wheel to pan, but you can change all these settings just like you can with Fusion, like Mechanical CAD. We only need one, so I'm going to hit escape and get out of that menu, and then I'm going to add the transistor as well. Stop it. Just components. Awesome. What was the name of that transistor? It was this guy. I'm just copying that name because I don't want to type it all out. All right, all libraries. So we're searching the whole device. Just gonna pop that in. There it is. There's the library. Double click. And there's the symbol. And we're just gonna drop that right there for now. Only need one, so I can hit escape and close the menu. So the timer is nice because the pins are labeled, but the transistor isn't. So you have to do a little bit of digging. I'm not going to show us this, but I went to the data sheet. I looked at the different models and the pin numbers, and 1 is our gate, 2 is our source, and 3 is our drain. So when we wire it up, that's just important to keep in mind. All right, what else are we going to need? We got the timer. We got the transistor. We need 2 resistors, 2 capacitors, well, 2 1 microfarad, 0.1 microfarad capacitors, and 1.01 microfarad capacitor, and then 4 just standard header pins to interface with the Arduino. And all of that is in the schematic we were looking at. I would have to reshare to show you again, but it's there. So I'm just going to start adding those things. Again, we can go to place components. We're actually going to go look at resistors, and you can see there's a nice little resistor library for us. That's got just a standard generic resistor. Invariant, you can drop down the menu and pick different sizes. So this is, again, like I pointed out right in the beginning, we have to keep in mind when we're making schematics that this is a physical part. So whatever you pick here is going to matter when you go to the layout phase. You don't want to pick something crazy. You don't want to pick something too big or too small. You won't be able to use it. It's got to be the one you want to buy. So how do we know that? So we're going to be doing surface mount resistors. So we've got a lot of options. Chip just means surface mount, and then you've got these numbers. So these numbers are the size of the resistor. So 0603 is 0.06 inches by 0.03 inches. So that's about 1.5 millimeters by 0.8 millimeters. So that's pretty small. And then you keep in mind, you can go way lower than that. So 0402 is 0.04 inches by 0.02 inches. These get really small. When I'm hand soldering, I don't go below 0603. Hand soldering anything below 0603 without a microscope is a huge pain in the ass. Even with a microscope, I don't go a whole lot lower than 0201, which is the next size below this. And even that can be a little annoying sometimes. So we're going to stick with 0603 components for this, and you'll get a better idea of how big that is when we move to the layout. So I just click that, double click, and bam, there's my resistor symbol. We need 2 of them, so I'm just going to drop in 2 resistors right there. This is just a generic resistor piece, so it doesn't currently have a value associated with it. If you imported a resistor model from DigiKey or something, it would already be the correct piece, but for us, we're going to label it. And we can do that by assigning a value using Fusion's tool. With Fusion ECAD, something that's a little annoying sometimes, the origin of the part is the plus sign. So you kind of have to find the plus sign. And that's where you want to be clicking to drag things around and stuff. Clicking on the wires isn't going to help. So we're going to click on the plus sign. We're going to give it a new value, 1K. And we're going to do that with that one too, because we need 2 1 kilo ohm resistors. All right, that takes care of the resistors. Do the same thing with capacitors now. Go to the included capacitor library. Just take a generic one. You can see there's all different ones. We're going to take the chip 0603 again, and we're going to need 3 capacitors. 1, 2, 3. Hit escape. And we're going to assign values just like before. The plus sign for these is right above the 2 parallel lines. It's a little hard to see. So we need 2 0.1 microfarads. So 0.1 U is 0.1 microfarads. And then we need 1 0.01 microfarads. That's for the VCC capacitor we talked about. Does anybody have questions or concerns or need me to repeat something? Cool. All right. So we're going to get started with wiring this up now. The power pins we'll do later. Right now, we're just going to get all the components in place. So I'm going to hit escape to exit out of the value menu. And let's see, what should we do first? So the control pin here, if you look back at that original schematic, again, I'm not going to pull it up. I know I wish I could, but it's a little annoying. That gets actually, oh, I was wrong. That gets the 0.1 capacitor, 0.01 microfarad. The VCC capacitor was this guy. So the small capacitor, we're just going to put at control. We're going to put it near, and we'll wire it in a minute. The 0.1 microfarad capacitor, that one is for either VCC or for our main charging and discharging capacitor that controls the timing. So we'll put this one near discharge for the charging one, again, based on that schematic. And then the other one will stick near VCC. The resistors, we got 1 resistor over by the output going from output to VCC. Not really sure what this one does, honestly. I think it's just part of the voltage divider that the device uses internally. And then our RL or RA, whatever one it was that we were talking about, that controls the rate of charging for the capacitor, is also going to go near discharge to help with that. And then this guy, our transistor, the gate, which is pin 1, is going to go to trigger, which is our input. That's way over there, so we're not going to move it over there. But I think we are going to stick it over here, because it's going to be pin 3, which was the drain, is going to end up going to ground, but pin 2, which is the source, we need to connect to threshold and discharge. So it's got to be around here somewhere. Making schematics is kind of a trial and error process. Like things aren't always going to look nice the first time. You kind of just have to wire things up and then move things around until they look good. So for wiring things up, that's the net button. And it pops up this little menu, gives you different options. I don't usually mess with these much because it's just for design. The actual traces we do care about, those will be in the layout section. All right, so ground is going to go to ground. We don't have to do that one yet. Trigger is our input, so we are going to need something going to the input there. I'm just going to leave that floating for now by hitting escape. Output, that one goes both to our output signal and to this resistor. So we are going to tie it to the resistor and leave a little bit floating for our output signal. The top of this resistor, I said, goes to VCC. And reset, we are also going to be tying to VCC because we don't want the device resetting on accident. So the reset is active low. So by tying it to VCC, it's never going to reset, which is good. VCC, we're going to do that later. And then discharge and threshold are where most of our connections are going to be. Control just goes to this capacitor, like I said. And then we've got the main resistor here going from power to the discharge pin. And as you can see, it accidentally, I got it into this capacitor as well. Usually you wouldn't want that, so you do need to be careful of it accidentally passing through something else. But if I wanted to fix that, I could grab it. Well, I guess I would have to delete the trace. Sometimes you can just fix it, but because of how I set it up, we'll move it out of the way. To delete traces, you just select on them and hit backspace. All right, there we go. That actually was fine though, because this capacitor is connected. That's the main charging capacitor. Discharge and threshold are connected together according to the schematic, which is cool. And then the output of all of this, again, this is all one node, is going to go to pin 2, which is the source on our device, our transistor. So this is not in the right spot. It's going to be a little hard to reach it. So we're actually going to move it up here, and we're going to use that mirror tool to move it around so that we can get a nice looking little schematic. Now it's kind of on the easier to connect. See? And then pin 3 was the drain, that's going to go to ground. And then pin 1 is going to go again to our input, which is trigger. But instead of drawing a wire all the way around, I'm just going to leave one floating for now. All right, so that gets us most of the way done. Oh, we got to do that power capacitor, which protects it. That just goes to VCC. Now we have to add power and ground. So those are also included in Fusion. You have to use the Fusion ones, I believe, because it automatically knows what to do with them. So I use supply. You get options for, there's like so many different supplies you can have, right? So for us, this is just for labeling. We're going to use 5 volts. And then we're just going to stick that in all the places it needs to be. So we need one there. That's our output, that's our input. We need one up here. And let's see, I think that's it. And we're going to do the same thing with ground. So place components, we're going to go grab ground. Again, you can have different types of grounds labeled for different quantities of ground needed, depending on how complicated of a design you're making. We're just going to stick that right on the ground pin. And then we need one. Oh, actually, yeah, we need one here. I kind of made that confusing. We need one here, we need one here, and we need one on pin 3. Again, this is just all based on the schematic. It's kind of annoying sometimes when you have a lot of parts. You really have to pay attention to what it is you're designing and how everything works. That's why I like going through the data sheet first and really making sure I understand how the parts work and what the circuit I'm designing does, That way it reduces the likelihood I make mistakes later. This guy could just go there. What else needs to be wired? We need to wire both of those up here. So it's going to ask me, do I want to rename this wire we made to 5 volts? And I want to say yes, because that's the reset wire. It can be tied high. All right, so that just leaves our input and output. And the way we're going to do that is with names. So we just click name. This is our output. So we're going to rename this to out. And we'll place that little name right there. And then we're going to do the same thing with our input pins. And now notice when I go over here and do that with this one, it asks me, do I want to connect them? Because it knows where to put wires based on the names. So even though these aren't actually connected in our little picture, because these wires have the same name, they're the same wire. So those are our input wires. So that saves us from having to draw a big long wire across the document. All right, we've got in and out. There's a couple other things we need. We need our header pins, and ideally you would want to put some test points on here too. So we're going to do that. So for the header pins, I'm just going to search Pinhead, which is the library that Fusion has already for us. And it's got all kinds of different pins we can use. We want, oh, come on. So we're going to want 1x4 because we need 4 pins total. And we're just going to use straight up and down pins. And these are what's going to connect us to our Arduino and our input and output. So that is something you have to include in your schematic because it's going to transfer this directly into our PCB layout, and we need to know what it is. So we've got 4 pins, and we're going to use that naming trick to make everything super easy. So we're just going to draw things out using the wires. 2 of them are going to get 5 volt and ground. So instead of searching for another 5 volt and ground, I'm actually just going to Control C and Control V to get me another one. I don't know why it did it like that, but we can move it. So that one will be 5 volts. Yes, that's cool. We're going to take this ground. Come on. And we're going to put that on there. And then we're going to name our input and output. And again, it's automatically connecting all of those for us. All right, now I want to add some test pads. These are optional, but if you're making a larger PCB, it's sometimes nice to have an exposed area that you can put like a multimeter or something on a signal you may need to debug. So this is just like something you kind of learn with experience thinking ahead. So we're going to go to test pad. And let's see. Yeah, this one looks about all right. What other options do we have? Yeah, I don't want to. All right, so we're just going to grab that guy. And we're going to put one on our important node over here. Awesome. Because that's the node that kind of controls everything. So if something's going wrong, it's going to be going wrong here. We want to see it. And when we add everything to the layout, it'll make more sense. It's pretty messy right now. So usually at this point, I would take time and like clean everything up. But in the interest of not making this last forever, I'm not going to do that. But basically, you can drag and drop these names. You can delete things. You can rename things. Just making everything look nice and easy to read. So we'll save it. And now we're going to validate it. So Fusion gives you a little tool to make sure you didn't miss anything or make any obvious mistakes. It's like a little syntax check for it. So ERC, electrical rules check. I'm just going to click on that. And it says, okay, we got some warnings. So what's going on? Power pin on VCC is connected to a signal. So yeah, that's whatever. U1 is this guy. it's connected to, oh, never mind. That was a good warning because we didn't connect this to VCC. Usually warnings are just warnings. It wouldn't crash, but it also wouldn't work. So it's just letting us know that we missed something. So we'll stick that there. It was saying the power pin wasn't actually connected to any power pins. It was just connected to this wire, but now it's actually tied to VCC. Thank you, ERC. We're gonna clear it and we're gonna run it again. All right, so now it's connected to 5 volts. That's good, that's what we want. JP1 has no value, that's okay, it's just a header. And we got no warnings and the errors were not important, so we are good to go. We're gonna approve those, clear them, I don't really care about them. We'll save again because we made a change. And now we can go transfer those directly to PCB. So it's gonna link everything through this document, so we have to keep this open, but we can just hit switch to PCB document, and it's gonna take everything we did and stick it over here. And now if we go back to our connector, we can see that we have a schematic linked to a PCB. So this is where like Fusion becomes really cool because you can keep everything organized in the same place as your mechanical stuff. And you can actually make a mechanical design, tell it, I want a PCB on this sketch, and then import that into your PCB and create a PCB shape out of that sketch, which is a super cool feature. And is one of the reasons I prefer Fusion 360 over something more professional like Altium, just because for what we're doing in like rapid prototyping and all of that, it's just super easy. All right, we got all these things. They're a mess. We have to put them on the board. So again, we got to find the origin. There it is, the plus sign. It's really hard to see. The white plus sign there on this pin. And we're just going to drag this onto our board. So the board is the black space. And we're just going to stick that up in the top corner. We're not going to use the whole board. So we'll trim it in a minute. As you can see, the purple lines are the wires that we made in our schematic. So anytime we update something in our schematic, it's going to update here for us. So let's see, we can rotate parts just the same. This is our resistor that was going from power to that other internal signal I was telling you about. I think this is our main charging resistor. So that's going to go here for now. And same with the schematics, like this is just trial and error. It's not going to look great the first time, but the important thing is getting it to work. Rotate things. Let's see. This is our ground pin up here. So we're going to actually connect things to ground differently. So it's going to make more sense for us to keep this guy nearer to the pin it's actually supporting. Same deal here. We would rather have this with our useful resistor, and then the ground connections will come later. With the schematics and the PCB, I do power and ground usually towards the end, just because there's so many different connections that are power and ground. If you try to individually do all of them, it'll take actually forever. So let's see, we got this guy going to ground as well. So we're just going to stick it near the pin it cares about. This is our transistor down here. As you can see, it's pretty small, so this might be a little annoying to solder. And we may want to look for a bigger piece, but for now, we're going to be using this. And this guy, oh, I don't know. Let's see, we've got ground, we've got our input signal, and we've got the internal signal. So I think we'll stick it near the internal signal maybe. We could do it over here and then move this guy closer. Yeah, there we go. Trial and error. Here's our test pad we made. So we can go stick that near our signal as well. Jumping around. Yeah, that looks like a good spot. And then our output pins. We'll put those at the bottom of the board. All right. So now everything's kind of in place. It's really hard to see things. So I'm going to go through and clean it up, just deleting all these names. We don't care too much about them because there's a different way we're going to name things for the actual document. And these names are just kind of to help us. And right now they're really hard to see. All right, now we know where everything is. So we've got to make our wires, we've got to make our ground, and we've got to make our power. So I'm going to do wires. And the way we route wires usually is through route manual. So Fusion and most other tools do have an auto router. But I'll be honest, it's not usually super good. And you usually have to go through and reroute a lot of things anyway. Employers are going to be much more impressed if you do have the technical experience of manually routing, because there is some, again, like process rules and design specifications that you want to be looking for. And it's better if you know how to do those manually. So some of those things, for example, are the trace bend. You don't ever want right angle bends in your PCB wires because electrons will get stuck. I don't know, like it's not good. So you have to think about traces as flat wires, right? That's really what they are. And when you have something flat and then it's turning at a 90-degree angle, you're losing a lot of surface area, and the surface area is what determines how much current you can flow through it, like the size of that flat wire. So we're not going to use 90-degree bends ever. We're going to use angle bends, and it'll automatically put those in for us. It just makes your design overall better. So as you can see, I click on a node here, and it's going to start routing me. So I want it to go here, so I'm just going to bring it to there. Super easy. That's the route. Now, the other things you can change are, again, that corner. You can determine how big it is, and you can determine the trace width. So trace width is directly proportional to the amount of current you expect to be going through it, because high current through a small trace is going to burn out the trace. It's kind of like a fuse. So the more current you have going through something, the bigger a trace you're going to need. And there's like charts you can look up for all of that. For us, since, again, going back to that data sheet, our design is like under, what was it, like 200 milliamps max. We're not using a whole lot of current. It's mostly just logic. So we don't need to have like a giant trace. 6 millimeters or 6 mil, which is not millimeters, is going to be fine for what we're doing. These ones I don't usually mess with. Via shape sometimes is relevant, and then you can determine your via size here as well. Vias is what we use to go through different layers of the board. So right now we're on the top layer, and I'll show you what that looks like in a minute. But that's how you route wires on one layer. So boards are made of layers. You can have many layers to the board. We're going to typically just do 2-layer boards, a top and a bottom. So we can like go look at all the different layers that's going on here. They're all right here. And it also, each layer you can think of as like holding the information for that layer, right? So the top layer holds the information for all the pads that go onto that layer. The top place layer, T-place, holds the information for all of the location screens that go onto that layer. So all the white drawings for the locations. T-names holds the information for all the white names that go on the top layer. So this is what the manufacturer uses to create your board. So having the right information in these layers is going to be really important. So we just always need to be conscious of what layer we're working in Fusion. Right now, again, we're on the top layer. We can hop over to the bottom layer. And as you can see, these changed to blue because these are through-hole components. They exist on both the top and the bottom layer. Our surface mount components are only on the top layer, so they're still in red. But these are all the things we have on the bottom that we can use. So we'll stick in the top for now. I typically do most of my work on the top layer. But sometimes, as you'll see, we're going to need to route wires through vias to get to the bottom layer, just so that we don't have any wires crisscrossing. And the more complex your design, the more you're going to have to do that, and the more layers you're going to have as well to enable that. So going back to the routing, this is really just do your best to make it look nice. It's going to automatically make sure you don't have any glaring issues. We're not going to do ground and power right now. We're only going to do signals. So this one's going here, and as well, it's going here. This is a pretty ugly schematic right now. Usually we'd want to make it look better, but again, trial and error. There's our output signal. That one's going to power. All right. These ones are going to be really annoying because they're all over the place. So let's see what we've got. If we move this guy, the wire will adjust with it. Come on. There we go. And now maybe we can take our input pin and trace it around. See, it doesn't like that. So we got to go around. And I just clicked it right here to tell it I want it to place there. And we're just going to bring that to the input. Now, I think you could probably see that this is an unnecessarily long wire. This is something you would want to try to minimize in your design. Like maybe it would be better if we move the pins over here. So let's try that, because this is a pretty bad design right here. So we're just going to undo that wire. And we're going to move this. Oh, I'm still in routing. All right, grab this. We're going to rotate it, and there. Now it's going to be closer to the pin we're actually trying to get to. Same with the output pin now. So you can kind of see, like, by using location and just like really strategically moving things around and trial and error, you can get a design that's much better. And this is what employers are looking for you to be able to do, and is not something that auto routing will teach you. Also, some auto routers don't even move components, so you have to kind of place it correctly the first time, which never happens. All right, let's see. These are input. Okay, input, that is really far away. Is there any way we can get that closer? Not a super efficient way. So the best thing we can do is just make it a straight line. Ideally, you would probably want to look for a better solution, but what we're going to do is show the bottom layer. So right now I'm drawing a wire in the top layer from the input pin. While I'm doing that, if I go over here and switch to the bottom layer, it automatically puts me as doing a via. And then I can place that via, and now I'm in the bottom layer routing a blue wire. So this is how you create wires on the bottom layer. And as you can see, I can draw that wherever I want, because I don't really have anything on the bottom layer. I only have the pins, and now I can connect that directly to that through-hole pin. So that takes care of that. That's ground, 5-volt ground, and ground. So I think we got all of our signals taken care of, and now we just got to do ground and power. And the easiest way to do ground and power is with a pour. So you'll often see ground pours in your designs, because having a ground pour or a ground plane is actually a really stable and efficient way of doing a ground for low current signals and for like DC signals especially. You typically don't want high current and like high current AC with logic to have the same ground. So you would do separate ground pours for those. But those are all kind of more advanced than what we need to get into today. But because we have so many ground signals, and you're always going to have so many ground signals, it's always just easier to do a pour. So we're going to do a polygon pour, and we're going to draw a polygon around our schematic here. Just trying to make it look as nice as possible. finish it off, and it's going to ask me what signal do I want to make this pour, and you type in the name that you originally were using, and now you can see that we have a ground pour on the bottom layer. This actually isn't where I want the ground pour because all of my surface mount signals are on top, but I wasn't paying attention and was in the bottom layer. That's okay, it's easy to fix. We just go back to the top layer and we do the same thing. But again, this is just like getting that feel for the layers and how everything works is a really important part of the process. There. So now we added this giant ground signal basically, and all of our ground connections were connected to it. So now the only things that are floating are the 5-volt connections, which you can kind of see like through the red. Notice how it automatically accounted for other signals, so it left plenty of space here. If you had a thicker wire here, it would leave more space, but it did connect to our ground pads for what we did want. So that's cool. We're actually going to put our 5-volt signal on the bottom layer. Again, there are definitely situations you don't want to do that, but for something small and simple like this, it's going to be easiest for us if we just do another pour on the bottom. Try to keep it the same shape for the power. Again, like you wouldn't want to do this with high current signals or really fragile signals like buses or like I2C lines, nothing like that. Like this, that's a bad idea for that. But since we're not doing any of that, this is all just transistor logic, we can get away with convenience, basically. So the name for this signal was plus 5 volts, and you can see it automatically connected to our plus 5 volts pin. What it didn't do was connect to our ones that are up here. It only connected to the through-hole ones because our surface mount components, again, are only on the top. So this is where we can use those vias again. So we'll go back to routing. We'll click on that, and we're going to put it onto the bottom layer, make a via, and then we're just going to connect it to the pad. And now you can see we have a 5-volt connection now. And we're just going to do that for our last few floating signals. If you have a large design, you want to minimize the number of vias you have. I'm showing you this because it's a good strategy to know how to do, but most of like the skill that comes with PCB design comes with doing things efficiently. So the more vias you have, the more like jumping between layers you have, the less efficient your design is. Same with like the longer the wire is, the less efficient your design is. So you want to make nice looking designs that have shortest wires possible. Everything is in a place that makes sense. Least amount of vias possible, because then that increases the complexity. So you don't want to go crazy doing this method. For what we're doing, since this is a small board again, it's really simple, it'll work. But for a professional design, you definitely would want to be careful of how you go about doing this. There are other ways. This one, actually, we can just draw it with a normal wire since it's right next to it. Same with here. So that saves us that problem. All right. What we're going to do now, we're almost done, is do another rules check. So sometimes you miss things. Sometimes things are like wires will be too close to components, or components will be too close together. And we can do, again, an electrical rules check or design rules check to make sure everything's okay. So we're going to hit that and check. All right. We've got one air wire and one clearance. So air wire is a signal we missed. Let's see where it is. All right, right there. That's easy to fix. Awesome. And going back to our rules check. Check again. Where did my tab go? Okay, it ended up over here for some reason. That was weird. Let's try it again. Oh, stop doing it. Basically, we still have a clearance issue. I don't know if you guys can see the separate window or not, but there's a clearance issue, and it's over here. So what it's saying is that we have a via too close to this pad. So it doesn't have the right clearance for manufacturing. And you can specify what those parameters are if you have specific manufacturer parameters. But to fix that, we're just going to move this via a little further. So it auto corrects everything. Do a rules check again. And down at the bottom, it says no errors. So this means our design is now functional. You can save it. The last thing I want to do is add labels to everything, because right now, if we go over to manufacturing and preview it, can you guys see this window? Awesome. This is what our PCB will look like. For one thing, this is way too big. For another thing, there's no labels. So we're going to fix all that. To fix the size, we're just going to drag the window. So this is like the PCB board itself that you're specifying. We're just going to move that so that it's more of a shape we're looking for. There we go. Preview again. And now you can see it's a nice normal circuit board. To add labels, it's super easy. We go back to, we go over to document and we make sure we're in T names. So T names is this top level of names that are going to get printed. And if we add text under the draw menu, we can specify font size. We can specify where it goes. It's super easy. So we're going to label our pins. So we've got in, that's way too big. That's better. We got in, that one is right here. We've got out. And then it was ground. And 5 volts. As you can see, we kind of have a little mess up here. It's just a little gross looking. So we're gonna get rid of that. There we go, that's better. It's still in the way of this pad though, so it's not an error, but it's annoying. So we're just gonna rotate ground. There, so now our pins are labeled. We can label all of our individual parts if we want. But that's really on kind of an as-is basis, depending on if you need it. As you can see, we got those pin labels in, but none of our components are labeled. So it might be a good idea to go through and be like 0.1U or 1K, 0.1U, 1K, whatever, for all the different resistor and capacitor values, just to make sure we do that right. Usually you would also name your test pad, but it's the same process as doing this. You just go into T names and you add text. Again, you're working in T names, so it's going to print it as text. You can also add screw holes. I believe that's in design. Yep, you can place holes. So if you want to mount your board to something, you can do that through here as well. But that's really it. So after this point, it's just making it look nice. It's making it, again, as nice and efficient as possible if you want to be showing this off to people. But at this point, it's technically ready to go. You have everything it needs to be manufactured. So we previewed it already, but the next step would be exporting it. So I use this one, Gerber files, the drill file, and then the assembly and drawing, which is again those layers. It's the information for all the layers we're using. Just doing that, we would save it. This is all the files we're going to get. It's a lot, but it comes as a zip folder. And then you just upload that zip folder to like JLC PCB or something, and they know what to do with it. I'm going to go back now to the slideshow. So we did this, we made it. We learned how to import parts. That was all I have for the tutorial. Are there any questions, anything you guys want me to go back to or repeat or show again? I'm happy to answer questions or anything now.
Did we run it without running?
I don't have any questions. You guys?
Unplug it.
No.
All right,
I have a
cool.
question.
Well, you know where to find me.
Actually, hold on. Does Evan have a question?
Yeah.
Oh,
So is it all
sorry.
at all common to run into issues with like, say, a specific part you're ordering doesn't have available, like layout files? Would you ever have to sort of create your own?
You would never have to create your own, but it is very likely that not everything will have parts files. So like, let's say I was looking for that transistor. I probably, should have shown you guys how to do this, but you're looking for transistors. Let's say we're looking for a JFET. We can search it like that. We can also just search transistor. And we want MOSFETs maybe. And DigiKey can handle all of this for you. So usually the filters I use, I want it in stock, I want a data sheet, and I want the EDA CAD model. So by checking that, you guarantee that there's going to be that file for you to download and import into Fusion. DigiKey Marketplace products are really expensive, so I'm going to say no to that. And then up here, you can put in the necessary design parameters. So like for us, for example, we were using p-channel. And then it's like just slowly filtering out the different things we were using, right?
Okay, cool.
Yeah, that's how you would do that. You can go in, get that part, scroll down, and it's guaranteed to have that EDA model as long as you check that filter.
Thanks. Also, one thing I've noticed about like Fusion in general is like when you're placing components, it's kind of locked to like a grid system. Like for example, when you're moving around the text for the silk screen, like you couldn't really get it exactly between, where you want it. So is there a way to get, I guess, like more granularity, get more like fine-tuned movement, or is it really just you have to work with what you have?
So that would be in the Fusion settings. Fusion has a whole separate section in its settings for your ECAD stuff. Like that's how I got my schematics into dark mode, for example. But so yes, you can play around with that. The reason I don't is just because it does help keep things organized. But yeah, you can totally play around with it to make it look nicer and easier to use.
Right. So if you change that, would that sort of like cause problems for other people with different settings working on the same document?
Good question. I don't know. I haven't done a whole lot of collaboration with Fusion, but that would definitely be something interesting to look into. Yeah, we can totally play around with that with Catbot stuff.
Yeah. That's all I have. Thank you.
Yeah, of course. Anything else?
Ryland, before you leave, we got the planetary working.
Yeah,
Yeah, it drives.
sick. Send videos.
Yeah.
Sure.
Okay, I got it. Load her back up.
Yeah. Thank you so much for doing the tech talk, Ryland.
Yeah, of course. I hope it was interesting, if not helpful.
Oh no.
Pretty
Yeah, thank you.
It's good they already made.
I like knowing that,
Now it's
just
more
having that
technical
ability,
working.
knowing that if I needed to make a
Oh, yeah.
PCB for any specific project I'm working on, now it's no longer a question for me. Like on how.
Yeah, it looks really intimidating, but it's really not that bad. You just have to, again, follow that design process and learn some of the tips and tricks.
Got it.
Okay.
Yeah,
we need to plug in that again.
That's I think I'm gonna head to work on finishing up what we have for 3 pounds for today. But thank you so much for doing the tech talk.
Yeah, of course.
And the recording, I believe you can just toss into the drive. Hopefully it doesn't take up too much of our storage.
Okay. Yeah. Would it be better to put it in the drive or the Slack?
If you put it in the Slack, it's gonna start removing other data
You could
to
do
make
it as
room
a-
for it.
Gotcha.
Unlisted
Alright.
YouTube video.
So put it in the drive first, and if that doesn't work, then the Slack would work.
I could also do it as a YouTube video.
Wonderful.
Yeah, that's a
Got
good
it.
idea.
All right.
I'm gonna open it up and see if anything.
I
Alright,
will.
cool.
I will see you next week for eBoard then.
Yep. For CatBot, I'm gonna be hanging out probably in the CatBot Zoom if you guys have any questions or want to talk about any CatBot stuff.
Yeah, we'll probably be back in the Zoom in like 5 minutes.
Sounds good. All right, see you guys.
All right.